stellar jets like this can only be seen within the Milky Way. But well beyond our galaxy, we often see truly enormous jets emerging from the compact centers of other galaxies. These galactic-scale jets are also millions of times further away. So how can radio astronomers see them at all? Never mind achieve such high resolution. 100 times better than the best ground-based optical telescopes. Radio waves have wavelengths thousands of times longer than optical wavelengths. That means that even the largest radio dishes cannot match, by themselves, the optical resolution of the human eye. However, radio signals from many dishes can be brought together and compared electronically, giving much better resolution.
Because we want to analyze these signals in the computer, the first thing we do is to digitize them. We do that in this rack of electronics here. You'll see one board for each of the telescopes, 7 in all. And then what we want to do is to compare the signals from each of the pairs of telescopes spread out across England. And we do that in a special purpose computer we call a correlator down here. And you'll see 21 boards in all down here, one for each of the pairs of telescopes or baselines in the array. But what do these comparisons look like?
As the Earth turns and the radio source is tracked across the sky, the waves arriving at any pair of dishes progressively move in and out of step with each other, producing an interference pattern, the blue lines. It is these periodic variations which carry information about the detailed structure of the source. In this case, it's actually a double radio source. Here, the image is synthesized from fringe patterns like this idealized one, simulating a single pair of nearby radio dishes. During the day, the pattern subtly changes, but when they're combined together, we see the first clue of a double structure. A longer baseline gives more fringes, and hence details on a finer scale are revealed. A pair of hotspots near the middle now. With more than 2 dishes, with an array of dishes, we have many baselines at different orientations simultaneously. As the Earth turns and the different views are added together, the structure of the central double source slowly becomes more evident. Longer recordings give better pictures. Finally, after further computer processing and image enhancement, even the fine jets can be resolved. It is these jets that are responsible for the commonly observed double structure. Giant radio lobes extending on opposite sides of an unseen active center.
The dish behind me is one of an array of 7 spread around Britain called the Merlin array. It's only when radio telescopes work together in that sort of way that we get such high resolution. Now, there are many arrays of radio telescopes around the world. Another important one is called the VLA, or Very Large Array, in New Mexico.
The Very Large Array comprises 27 antennas. They're arranged 9 on each of 3 arms, one arm to the north, one arm to the southwest, one arm to the southeast. Along these arms, we can move these antennas on transporters up to 21 kilometers away. There are a number of fixed pads along these arms in which the antennas are placed. By putting the antennas on these positions, we collect information from each antenna, multiply the signals from each antenna from all other antennas, and collect 351 pairs of information which are used to make images of the radio sky.
Goal 17.
Antennas spread way down the arms give us high resolution for fine detail, and when the antennas are close together, we are looking at a very broad scale structure for low resolution and studies of large angular areas.
So we can only get the highest resolutions if the telescopes in an array are really far apart. The telescopes in the Merlin array are much further apart than those in the VLA. The nearest telescope to this one in Cambridge is actually about 100 miles away in Worcestershire. But the really clever thing is when we couple one array with another one that's a huge distance away. In that way, we get truly incredible resolutions.
Here, for example, is a Merlin image of 3C273. But linked up to VLA across an 8,000 kilometer baseline, we can see even finer detail closer to the nucleus itself. The technical breakthrough that made this possible was the development of extremely accurate clocks, atomic clocks based on hydrogen masers. Now it became possible to bring the signals together simply by mail. The digital tapes are recorded at widely separated locations, but at a precisely known time. This means the VLA can extend its baseline from a remote antenna in Hawaii in the Pacific to others across the Atlantic in Europe. And Merlin antennas in England can be combined with others in global arrays, enabling distant radio sources to be mapped with incredible resolution. This technique, called very long baseline interferometry, has given radio astronomy the edge in high-resolution imaging. For example, in these images of 3C273 taken only 2 years apart, they could just detect movement of the matter down the jets, which must therefore be moving very fast, close to the speed of light.
The high velocity of the jets has a funny consequence that the light is beamed in the forward direction. And so a jet pointing at us is not only blue shifted, but appears much, much brighter than the receding red shifted jet. So at any angle other than the plane of the sky, the oncoming jet will be much, much brighter than the receding jet, and we may only in fact see one-sided jets.
Astronomers have now observed hundreds of jets emerging from galaxies at all possible orientations. Most of them indeed appear one-sided. Is the receding jet really dimmed so much we just can't see it? What we can see is the longer jets that twist and turn and bend in bright, writhing arcs, as if blown by some galactic wind. Others may even collide and interact with each other. They may look different, but they all seem to originate in the same way. A dusty torus fueling a very bright disk of material, spiraling, or as astronomers say, accreting, onto a compact core at the nucleus of the galaxy. Often long, narrow jets stretching thousands of light years beyond the parent galaxy.